All right, thanks a lot for coming back to this first afternoon talk about the quantum random oracle model. So this is part 1. There will be a part 2 given by Christian Mayens over there after the break. And I invite you to join the quiz. The quiz is not quite as exciting as yesterday, where you have to answer quickly on time. But nevertheless, it will include some interaction with the audience, which the first question is already up. So I strongly suggest you get, you don't have to register or anything. The question is just what kind of background do you have? Because I'm actually curious to hear what you guys know already and what you don't. Because as you saw from this morning, we are going to start diving into the quantum world, and this is already a bit of a deeper dive. What's ahead of us? As Stefan mentioned, I'm in Amsterdam. I'm a professor in theoretical computer science at the University of Amsterdam. Let's see if this works. Yes, here that's the logo of the University of Amsterdam. I also am now the director of QSoft, which is the Research Center for Quantum Software and Technology in Amsterdam. And I'm going to shamelessly use this stage to promote a little bit our hiring process. We are looking for faculty members actually very soon. So if you keep an eye on our website, there will be an ad up soon. But even maybe more appropriate for most of you, if you're interested in doing a postdoc in the Netherlands, in Amsterdam, or join us as a PhD student, you're very much welcome to get in touch. Furthermore, we're actually starting a new program in quantum computer science, so right down the alley of this summer school. So if you're a talented master student with a math background, or you may be doing a bachelor right now and you're wondering where you want to do your master, well then, actually that's a great opportunity to come join us in Amsterdam. There's going to be a new building as well, and yeah, it's exciting times ahead. So, what I'm going to tell you today is I'm going to start off introducing the classical random oracle model to you. You've already heard a little bit about that stuff, and then we're going to transition into the quantum world, and we'll see where we go there. So, the classical random oracle model, before I do that, now we got more serious. I want you to answer this question. A random oracle you can see as a random function. Let's say from n bits to n bits. And the first simple question I would like to ask is how many of these functions are there actually? So last chance to kind of get onto the board. I mean, I'm sure there's way more people than 51 in this room. So just scan the code. I hope it's still visible. Yeah. And let's see actually a little bit about your backgrounds. I see. Okay. About 40% have done a master program in mathematics, but there's some physicists here as well, and then half of the audience is from computer science. And there's a few others. I'm actually curious about the others. Who is other than that? Who dares to speak up? Anonymous others. Yeah? No other? Come on. 5 people said they didn't do any of this, so what did you do? Just shout. All right, I think they're kind of embarrassed, maybe. If I don't want to push it. All right, first question. Mathematical questions. How many functions are there that map n-bit strings to n-bit strings? For now, the results are hidden. And you have 5 choices, multiple choice. Is it n factorial, 2 to the n, 2 to the n factorial, or 2 to the 2 to the n, or 2 to the n times 2 to the n? So let's see if you remember something about your mathematics background. I'm gonna answer the question as well on the slides after that. Let's wait a little bit more. There's 30 respondents. And let's have a look. All right. So I'm afraid, as usual, that actually the majority of people has it wrong. Because the right answer, as you're going to see in a second, is the last one. So there's a lot of people who think other things. So let's see why this is the case. So you want to count the number of functions from n-bit strings to n-bit strings. What you can do to specify the function is write down a truth table. Just write down for every input what the output is. So if you do that, you will end up with a table like this. So you write down this is the output. These are the n bits output on the input 0. These are the n-bit outputs on the input 0001. And now we can count. So this function has 2 to the n inputs, possible inputs. So it has 2 to the n rows. And for every row, in every row, we have to specify n bits. So this table, this truth table, has n columns and 2 to the n rows. And every time we change a single bit in this table, we get a different function. Because then we assign a different output to an input. So number of different functions is the ways to fill in this table. There's n times 2 to the n entries, and they're all binary, so you always have a choice of 2 for any of these entry, and you'll end up with this number. So 2 to the number of entries in the table, which is 2 to the n times 2 to the n. And as you can see, this function is crazy big. So already for n equals 6, you get something like, well, this 6 times 2 to the 6 is something like 384, I think. And so 2 to the 384, this is bigger than the number of atoms in this universe. So just the number of 6-bit strings, the number of functions mapping 6-bit strings to 6-bit strings, it's like something that we cannot imagine. And of course, this is doubly exponential growth. The issue is that this n here is in the exponent, and not in the exponent, but in the exponent of the exponent. And that's why this function basically explodes. All right, so that also means, in particular, that if you want to specify such a function, you already have to write down an exponentially large table. It has 2 to the n rows. So just completely specifying an arbitrary n-bit function, mapping n bits to n bits, actually will take you exponential time. So we cannot really easily kind of specify such functions, arbitrary such functions. In order to understand what the random oracle model does is, well, you have to know something about hash functions, and I guess most of you have seen hash functions. Formally speaking, a cryptographic hash function maps an arbitrary sized string, so this is what I mean up here. So if I say 0, 1 to the star is like an arbitrary sized string, so in particular it could be the empty string, or just 1 bit or 2 bits. Any number of bits you can throw into the hash function, and it will spit out a fixed size output, n bits. And you can think of the output of such a hash function as like a fingerprint of the message. So here's an example, maybe a very famous example of SHA-3. So later when you download the slides, you can click on these links, and I think this will send you to Wikipedia. That just specifies what this function does. And so you can kind of take the ASCII encoding of the string, and out comes a 256-bit number. So this is the fingerprint of that particular message. And a cryptographic hash function is good if it kind of looks random. So in particular, if you change a single bit in the input, so instead of dog, you like write Dorf, then you get a completely different looking fingerprint. And so this is just like if you run that function, well, you will get different outputs. And ideally, we want that such an ideal hash function, it should behave as a random oracle. So that's the thing that we just saw, which basically assigns random outputs to every different input. So whenever you put in something new, you will get a completely random output. Of course, a fixed function is not a random oracle. It's just a fixed function. It's specified on Wikipedia. But we kind of want to model it like that. And this is exactly what the random oracle model does. So here we go. So a little example is we want collision resistance. So, and we can actually prove that for a random function. So here's a theorem I will prove for you. In a random function, it's difficult to find 2 colliding inputs. So formally, if you have an adversary A that makes Q queries to this function, to this random function, we have that this holds, namely that, well, this A can make oracle queries to F, outputs X and Y, and we want that it fulfills this predicate that X is different from Y, but F of X is equal to F of Y. So this we call a collision, so 2 different inputs that map to the same thing. And we can show that the probability for such an adversary to exist, or to succeed in this task, is actually upper bounded by Q squared over 2 to the n. So in particular, if A makes only polynomial amount of queries, then this is a negligible term. So if you increase n, then it will be very unlikely that you succeed to find 2 colliding inputs. And here's a kind of easy proof of this statement. So let x1 to xq be the list of A's queries. Without loss of generality, we can assume that A makes different queries, because whenever A queries the same thing again, it will get the same answer, so it's kind of useless to do that. So let's just write down the list of all these possible queries, x1 to xq. And then, if you have a random f, well, then, as we just saw, the outputs f of xi, they are independent n-bit strings, because for every different input, you get different outputs, independent different outputs. And the probability that two of these collide, n-bit strings that collide, is 1 over 2 to the n. You fix one, and you kind of want to match all the bits of that string, so the probability of that happening is 1 over 2 to the n. And if you have such a list of q entries, well, there's q choose 2, so q times q minus 1 over 2, so pairs in that list. And so this is roughly like q squared pairs. And so by a union bound, you can argue that, well, this probability that you find two that collide, if they all have random outputs, is upper bounded by this. So pretty easy, straightforward proof. I hope everybody has seen proofs like this before. All right. Now, one word, like why, kind of to motivate the random oracle model a bit further, is the case of digital signatures. So we already seen yesterday some example of a signature scheme. Just back, I mean, like on high level, the idea of a digital signature scheme is that the secret key holder can sign messages, but everybody can verify signatures. So in a public key signature scheme, you have a key generation procedure that allows Alice to generate kind of a key, a public key and a secret key. Public key she can distribute to everybody, secret key she keeps herself. And then, so in particular, eavesdropper and Bob, everybody can get the public key. And then she can kind of sign a message. So if she has a big message she would like to sign, well, then she can use her secret key to generate a signature, a digital signature. And it has the property that if this is sent over, even over an insecure channel, then Eve, who does not have the secret key, cannot mess with this message. So Bob, he can then verify using the public key that this message has not been changed in transit. And it originates from somebody who has the secret key, hopefully Alice. Okay, digital signatures are really used all over the place. And I don't know, I'm curious, maybe some of you actually have better numbers. So the only kind of slide I know that exists about this, where somebody has actually sat down and tried to enumerate the number of users where digital signatures are used every day, is back in 2014 at QCrypt, where Bart Preneel presented these numbers. And just some rough counting, like, I don't know, all our mobile phones, PCs, etc., they use signatures. He estimated this to be more than like 3 billion devices. Smart cards, all our payment cards, access cards to building, etc., they use digital signatures. Passports, web servers, I think these are now old numbers, but you easily get into like billions of digital signatures that are used maybe every day even. So yeah, so like there's huge numbers, and maybe the signatures are even kind of more widely used than public key encryption schemes. So it's a very important primitive, and the fact that there's these huge numbers of users means that you want to make them efficient as well. No, you don't want these operations to cost a lot of energy or power, money in the end. So well, as we know, those they involve some mathematical operations, and in particular the ones that we use nowadays, they are insecure against quantum attacks. We've just seen Shor's algorithm this morning, and they basically break the currently used algorithms or variants of these quantum algorithms. So it's a good idea to follow what we call the hash and sign paradigm. So instead of signing this huge message here, kind of encoding this into a very big number and do the heavy number theory in it, it's easier to kind of hash this message first down to a smaller fingerprint, and instead of signing the original message, signing the small fingerprint instead. So obviously this will save you a lot of work if you do that. And one can actually prove this theorem that if H, again, is modeled as a random oracle, then this paradigm, which we call hash and sign, is secure. And here's a little sketch. So again, we can think of these queries that Eve makes to the random oracle as x1 to xq. And then there's like two cases you have to distinguish. Either she finds collisions in H, So then she was kind of lucky and she kind of broke cryptographic property of H. Or if there's not collision, well then this hashing first actually is as good as like signing the original message. So somehow if the original scheme, the original digital signature scheme was secure, then also this new hash and sign scheme is secure. And so that means you can provide a reduction to the original security of this digital signature scheme. So this is obviously a smart thing to do, if you can. It will save you a lot of well, bandwidth, but also computational power, money in the end. Okay, so here we go now to a more formal definition of what the random oracle model actually is. And I've stolen this slide from my academic brother, Stefan, who is now paying attention. So the random oracle model is, again, it's actually linked down here. If you click on it later today, you will find old slides by Stefan uploaded to some SlideShare site where I basically just took them. So the random oracle model is a heuristic. So it's kind of, it's a model where we model hash functions in cryptographic proofs. So informally, and we've seen these schemes, like for instance this hash and sign, where, so that's what we call the protocol, that uses a hash function internally. And then we have an attacker that kind of interacts with this protocol, and the attacker simply knows H. He knows what kind of hash functions are used in there. So this is what happens in the real world. But now we kind of model this formally in the random oracle model by having the same setup of this protocol that uses a H function. But now we do something quite strange. Namely, we kind of introduce an additional, we kind of look into the adversary and check whenever he's, or she in this case, is interested in using the hash function, we can supervise that. So somehow it's a very controlled way how we allow the attacker to interact with this H function, with this hash function H. So formally, every call to H of the attacker is replaced with a query to a random oracle. So that means we can really observe the queries that this attacker does. So note, this is not something that we can actually do in practice. Actually, in practice, we don't know what the attacker does. It just knows the hash function, and it's out of our control. But in the random oracle model, we have control. We kind of see what queries and what answer the attacker gets from the hash function. So it's not a very natural model, but somehow it's kind of what we do. And it has its ups and downsides, which I'm going to go over now. And actually notice that what I did before, what I showed you before, this hash and sign, this is actually a proof in a random oracle model. I mean, it's also stated in the theorem. It says if H is a random oracle, then hash and sign is secure. And the proof goes like, well, let's write down a list of Eve's query to H. So we were already looking into what Eve does. So somehow, kind of under the hood, I already made you operate in the random oracle model when proving this. So, maybe a quick word to motivate further the random oracle model is how to build hash functions. So, maybe it's just a quick show of hands. Who has seen this before? Merkle-Damgard construction? Maybe half, a bit more than half. So our Stefan and my academic father, Ivan Damgard, back in when I was just born, they came up with a scheme of how to build hash functions. And the issue is, of course, that a hash function, as I said, it takes arbitrary sized inputs. So arbitrary sized strings. So how do you deal with that? Well, what you usually do is you kind of chop it up in smaller chunks. So in particular, you have some secure building block, and it's often called a compression function. So it takes 2n bits and maps it to n bits. And then you can take your arbitrary sized message, you chop it up in blocks, and then you just keep running this. You initialize your construction with some fixed value, and then you keep running the compression function. So every time you are transferring n bits to the next, and you'd feed in new n bits from the chunk of your message, and you keep doing this. Sometimes you have to kind of start special and end special, but in the end what comes out is the hash function. So that's kind of a standard way, one of the standard way of building hash functions. And So one could now kind of study, well, one does study security notions for this. An easy one is collision resistant. So this is actually a very nice exercise that I highly recommend if you haven't done it before. For instance, if you can't sleep tonight because it's too hot, just like solve this little exercise. If F is collision resistant, so that this is the compression function, then so is this bigger construction here, obtained by, if you do Merkle-Damgard on this compression function and you know that F is collision resistant, then also the overall construction is collision resistant. That's one of the very nice features of this construction. So this is kind of basic. Like more advanced security notion would be so-called indistinguishability. So this would assume that if F is a random oracle, so if this compression function just is a random function, then the input-output behavior of this whole hash function built in this way is random. So in particular, what we mean is like no efficient adversary can distinguish the interaction with the whole age from an interaction with a random oracle. And if you've done that before, then also this one is not going to be very hard. Yes, I see a question up there. I don't know if there's floating microphones. Yeah, up there.
So in the second result, you assume we don't have access to the inner building block, right?
Exactly. That will be the next slide.
Oh, okay.
Perfect, yes.
Okay, then
yes, indeed.
Let's continue. Okay,
yeah.
Thank you.
Okay, so this one is called indistinguishability. It's also not that hard to prove. And so you have this real and ideal world. So in the real world, you have a distinguisher that tries to distinguish this construction from a random oracle. That's kind of what this, that's like just an illustration for indistinguishability. And now comes what you just suggested. That's a stronger notion. It's called indifferentiability. So there, you kind of have more things playing. In particular, so this is the picture from the last slide. But now you also have access to the compression function, to this F. Because realistically, you know what this F is. No? Again, if you look up a particular hash function, it will specify this F. So the distinguisher not only has access to the whole construction, but he has access to this building block. And indifferentiability asks for something more demanding, namely that, well, if F is a random oracle, so if this building block is a random oracle, then we want that there exists a simulator such that no efficient distinguisher can distinguish between interacting with the combination, the real thing, like F and the Merkle-Damgard construction, and this, well, this simulator and a real random oracle. And the funny thing is that now the simulator also has access to that random oracle. So when you do this kind of proofs, what you actually do is you kind of maintain some lists. So you kind of maintain queries that the distinguisher makes to this building block, and you might also sometimes ask inverse queries. So there's several lists you have to kind of maintain in order to make this proof work. But yeah, that's the typical thing that you actually want to prove. This kind of argues why, say, this particular Merkle-Damgard construction is secure. Yes, question, Shweta? Microphone, yeah, almost there. Yes.
So in this slide, like in general, a simulator need not simulate a random distribution, right? So in this slide, it seems a little bit weaker than saying that this construction should look random, because the existence of a simulator does not mean that it's giving you a random looking distribution.
Yeah, but I think if the simulator wants to have a chance to actually be indistinguishable, and this is a random oracle, then
no,
well,
the F part, I believe. So
yep.
you know, the F is sort of being substituted by the random
yep.
oracle on the right
well,
side.
Well, actually, not exactly. So you still want that the constructed thing is a random oracle, but the simulator is now also allowed to query that random oracle. So you kind of have to adjust things so that this building block looks real to the distinguisher.
Okay, maybe I'll
yeah, it's a bit trickier, and it's more demanding, and you actually have to work. But you can, for instance, for the Merkle-Damgard construction, you can pull off this proof in the classical.
My worry, I mean, I'm sure I'm missing something, but the question that I have is that let us say, for instance, that the Merkle-Damgard construction was not emulating a true random oracle, but just something simulatable. like let's say, from a different distribution than uniform. In that case also this definition would apply. So I think the question I have is just that, this is not specifying the truly random distribution, the uniform distribution.
Yeah, I think this. Yeah. So Mo, if you manage to show this, then this interaction here should just look like a random oracle, and you have to adjust the queries that the distinguisher would make to this inner building block to be consistent with that behavior.
I think the confusion is that the Greeks over there, they are a random oracle. Right?
Yes, the Greeks. So this is the Oracle of Delphi. Maybe I should have mentioned this. This is the actual real random oracle. That does not exist in the real world, but this is the random oracle.
I have, unless Shweta wants to ask something more.
No.
Oh,
Okay, so one thing that's wondering me is that we are kind of doing it from the other side. We are assuming that the Merkle-Damgard construction is the random oracle and simulate the building block. And we could approach it from the other side to say that we just have the random oracle for the building block and use the oracle to then we simulate the Delphi Greeks. And what is the reason why we are doing it the other way around? Because it feels way more complicated to simulate it that way.
Yeah, I don't think I have a good answer for this. Maybe looking at experts. No, but I think there is a good answer, so I'll try to come up with it for you. Yep. All right.
Thank you.
More questions? Sorry. Yes, one more. Oops.
That's kind of what I wanted to ask actually at the beginning previously. So you just said we have this result for the Merkle-Damgard?
Yeah.
Because I would disagree, because the hash length extension attack, if you do that.
Yeah, you have to be careful in like how you do the actual construction. Indeed.
There's like a different, like
Yeah,
original,
so
the old one would be broken, but there's like some.
Yeah, so fixed size, so it is easier. For instance, if you, but yeah, one has to be careful.
Okay. Okay.
No. All right, so I'm coming to the kind of towards the end of the classical random oracle model, and overall there is. Well, there's some criticism. Again, I think this is from Stefan's slides again. And again, he pays attention. So there's the problem, one of the criticism I think that was mentioned earlier in a previous talk is that there is a digital signature scheme that can be proven secure in the random oracle model, but whenever you try to instantiate the random oracle model with a specific hash function, then it's not going to be secure anymore, which is obviously very strange. I mean, you don't want that, so it's kind of illustrating that this is not a good model. But on the other hand, it's also this particular example is very artificial, so it's not somebody that would not something that one would actually use in practice. And so, and in fact, there's simply no realistic examples known. So commonly, we think that a random oracle proof is better than no proof, and practical schemes are using hash functions. So, because it makes stuff way more efficient. So we also saw in Shweta's talk, it's kind of nice to avoid the random oracle, but you will have to pay for it. Usually it makes it way more, harder to implement. It will be more difficult to compute. So it's kind of the best we have. So, yeah. Okay, good. Then, where is it used in practice? Well, all over the place. And again, I invite you to go to the quiz, because this is a good moment where I'd like to kind of check a little bit on what your background is, what your background knowledge is about several things, namely what I'm going to talk about, the quantum random oracle model. If you have seen the Fiat-Shamir transform before, if, maybe I should not put this in front of the QR code, but I think it will just work if you go back to where you were before. Basic quantum concepts. So if you have seen, or maybe I hide this for now. So if you've seen, if you've never seen quantum stuff before, if you've seen it the first time this morning, then maybe you go for a 1, which would be not familiar. And then I'm going to show a few tools, namely T-wise independent functions, if you've heard of those before, or one-way to hiding lemma. So this is kind of the outline for the rest of my talk as well. So I'm curious to hear like how much you already know about these things. And while you enter this, I kind of, well, I want to mention that, yeah, as I said, in practice, and in particular in these NIST, upcoming NIST standards, hash functions are used all over the place. So in particular in the Fiat-Shamir heuristic, which was explained yesterday and which I'm going to quickly recap, but also that's for digital signatures, but also for encryption, KEMs, so key encapsulation mechanisms, are often built using this so-called Fujisaki-Okamoto transform, which also involves hash functions. And I was already sketching this indifferentiability proofs, and there's many, many more instantiations where the classical random oracle model is used. So, yes, maybe now is a good time to actually show the statistics. Wow, you're back to a lot of people. It's great. I think there's even a radar chart. So you can see that people are quite familiar with basic quantum concepts, which is nice. And this will help also for the rest of the talk. People have seen the Fiat-Shamir transform, at least, say, half of the people. And maybe the other stats, that's so interesting. Yes. Oh yeah, here you see the actual distribution. But nobody has seen T-wise independent, well, hardly anybody, nor one-way to hiding lemma. So, of course, you're going to learn that right now. Interesting. Okay. So, yeah, here's the quick recap from yesterday, and I just took Khan's screenshots from Khan's slide. If you remember, he showed us how to do zero-knowledge proofs, how to prove in zero-knowledge that you know a certain small secret. So there was this three-move called Sigma protocol, where this allows to prove this in zero-knowledge. And this is the basis to build a digital signature scheme. In particular, the Fiat-Shamir transformation, it does this trick that instead of having this back message here from the verifier, where he has to choose a random challenge, what you can do instead is you apply a hash function. So just take a hash function and map the first message that you get, this W, and the public parameters to get this challenge yourself. So this is a way how to transform an interactive protocol into a non-interactive protocol by picking the back message yourself, just hashing the first message. So this is what we call the Fiat-Shamir transform. It inherently involves a hash function. And then in the proof, this was like a quick argument that this is actually zero-knowledge in the random oracle model. So I kind of think just quickly mentioned, well, there's a simple entropy argument to show that we will never overwrite the random oracle. So you do kind of program this hash function to be some value that you like it to be. So you see this uses tricks. It really kind of looks into the adversary and it kind of programs stuff. It feeds particular answers to the adversary so that we in the reduction and the people who prove the security are fine. So these are tricks you can play in the random oracle model. And well, they're used for practical schemes. But now I'm going to tell you that we're actually in trouble because it's not that easy after all. And why is that? Well, it's because if you do post-quantum cryptography, and I think that's the purpose of this school, actually, so we want to be safe against future quantum attackers. So even those who can run, who can use the tricks that Julia introduced, and then also run Shor's algorithm and do all kind of nasty computations on their quantum computer, well then, in particular, they know this hash function, they've looked up the description of SHA-3 on Wikipedia, well then they can also run this function in superposition. If you have a quantum computer, a working one, well then, you just take the function and you run it in superposition. And what we actually need to do when we work in the random oracle model, we have to give additional power to these attackers. Namely, we have to allow them to make quantum queries to this classical function h. So before we were just allowing classical queries, like here specify an input, I will give you the output. Now, if we consider quantum attackers, if you want to be post-quantum secure, then we actually have to allow them to make queries in superposition to this function. Motivated by the fact that they can just, look up a description of H in the real world and run it on their quantum computer. So this is something that we realized back like more than 10 years ago in this paper. And unfortunately, it kind of invalidates many of the existing random oracle proofs. So a little bit more formally, what an attacker does, if he queries the random oracle in superposition, well, it's using, well, it's running this quantum operation where you just evaluate. So you put in a value x and a value y, and x is preserved. So and then f of x is XORed to y. So it's the standard way of evaluating a function f, in this case a random oracle, in superposition. And well, maybe the most simple example is just if you put your quantum register x in a superposition of all possible values, and you can do this easily by starting with the all zero state and just applying Hadamard gates to all of your qubits. And if you have n qubits, you will actually end up with what we call uniform superposition over all possible inputs x, over all n-bit strings. So this is this state. And then you do one call to this oracle, so you evaluate the function coherently over the superposition of all the inputs. So basically this will put all the outputs of f in this second register. And so with a single quantum query, Eve can access all function values, all outputs in superposition, just with a single query. So you can imagine that this, well, this is not something that we know how to deal with if you have a classical random oracle proof. Because there we often, as you saw, we write down like, well, let this be the list of oracle queries. But if the first query already queries all values in superposition, then we don't really know what to do. Actually, by now we know, and I'm going to tell you. But first about the trouble. So the trouble is that basically just classical ROM proofs, if you don't change anything, they break down in the quantum random oracle model. In particular, a lot of these NIST schemes, they come with random oracle proofs because they use hash functions. But I mean, the point of it is being post-quantum secure. So in fact, you will have to provide security in the quantum random oracle model, or if you want to be secure against quantum attackers. And so you have to work harder. You have to kind of circumvent these problems, because we saw before we just can program the random oracle. We can simulate the random oracle towards an attacker classically. That's very easy. It's called lazy sampling. We can extract stuff from answers of the adversary. Actually, Chris Mines is going to talk about this. We can rewind attackers, so we can replay some values. And this is all things that we don't know straightforwardly how to do this in the quantum random oracle model. So in principle, we have to go and adjust all the random oracle proofs to see whether they actually still hold in the quantum random oracle model. Yes, a question? Yeah, so the random oracle we would usually call the hash function itself. So a hash function is often like SHA-3 is just a fixed function. But in the random oracle model, we assume that this hash function is a random oracle. And a random oracle is really identical to a random function. Yeah. Yes, another question up there? Oh yeah, I should repeat the question.
After a uniform superposition query, doesn't the random oracle in a way instantiate itself to a fixed function because we query all the values?
What do you mean by instantiate itself?
Well, if we are essentially querying a large number of values in a single query, and once we query a random oracle, it remembers what it answered.
Yeah, yes. I mean, this function is fixed, so you can query a random function in superposition, and you will get the superposition of all the outputs. Yes, so it's there.
I mean, I'm asking because earlier you mentioned that that there are schemes that don't work if we instantiate the random oracle with a great function.
Okay, I see. Yes, actually, yeah. So that, yeah, Nico.
Could you speak to the mic?
Yes, maybe.
maybe this is a good moment to point out that such a superposition query, if the random oracle, say, has 1 or n qubit output, you really just learn n qubits and not the entire. I mean, the response doesn't encode the entire function table. This is like the Holevo inequality.
Yes, maybe that's a good thing to point out, the Holevo bound that was also mentioned this morning. I mean, what you have is you have a registers of n qubits that contains all the function output values in superposition. So it's not that you can choose which one you want to know of this. What you can do is you could measure it and you will get a random one. But that's the problem with quantum information. It's kind of, you can easily put stuff in superposition, but it doesn't mean that you can do useful things with it. And that's actually also why we can usually still save ourselves and kind of fix classical random oracle proofs, as you will see in the rest of the talk. Yeah. That is also what you meant, Nico? Yeah. Okay. Yeah. All right. So, where do we go from now? Yes, so I'm going to introduce 3 tools to deal with quantum random oracles. And the first one is so-called Q-wise independent functions. So most of you have not seen this, according to my poll. It's not scary and it's also not quantum, so it's good to remember. It's simply a property of a function family. So let's say you have a subset of functions from n bits to n bits, and they're called t-wise independent. If you take t distinct inputs, x1 to xt, then you look at the output values, then they are independent and uniform if you sample f from that subset of from that function family. Yeah, so it's just like if you look at kind of the orbits of t points, then they behave independently and uniformly. So for instance, if you take f to be the set of all functions, so if you just random functions, then this is clearly true. But hopefully we want to have such function families that are smaller than all the functions. Here is an example of such a smaller family. You can basically just take polynomials. So if you take the family that is given by, well, polynomials of degree t, where you pick these coefficients a0, a1 up to at minus 1 as elements of, well, the field 2 to the n, and you take t of those, then, well, as you can, I think, easily convince yourself, this family is t-wise independent. Because you need, in order to determine all these coefficients of a polynomial of degree t, you need like t points. I guess this is degree t minus 1, so you need t points here. There's t values that you need to determine. So if you have evaluations at different points, so if you start with a list of x1 to xt, and you vary over these functions, well, then actually all those will look independent and uniform. And this function family is much smaller than the, I mean, you only need to specify these coefficients, which is way less than like specifying arbitrary functions. Yeah, so this is an example of how to build a t-wise independent function family. And here's a theorem that if f is a 2q-wise independent function family, so think of q as not the number of queries, but something small, then for any q query quantum algorithm A, the probability that this adversary can distinguish a fully, I mean, if it has access to a fully random function, or has access to this function sampled from this 2q-wise independent function family, is going to be equal. So basically you cannot distinguish these two. So this provides a way to simulate a random oracle in the quantum random oracle model to an attacker. So notice this is maybe, yeah, I should have said it before. In the classical random oracle model, this is very easy. Simulating a random oracle is like whenever the adversary asks you a question, you sample a new value and keep track of the stuff you've answered before. Whenever he asks the same thing, you answer the same thing. So that's kind of lazy sampling. But here in the quantum case, well, actually, yeah, so this holds for a quantum algorithm. It's not so obvious because, again, in the first query, they could already ask everything in superposition. So this gives you a way to actually deal with this case. So if you have a bound on the number of queries that an attacker is going to make, then you can kind of fool the attacker into believing that he's interacting with an actual random oracle by just doing that with a 2q-wise independent function family. So I see a question up there.
So just to make sure, when we are saying independent and uniform, we are treating this with respect to the probability of sampling from F?
Yes, yes, indeed, that's this.
And the x1 up to xt are fixed and we don't consider them?
Yes, fixed and distinct, yes.
Okay, thanks.
Yep. Okay.
Another small question.
Yes, more question.
Theorem is a real equality, or is there some?
It's really equality.
Okay.
You cannot distinguish it, and I'm gonna prove it now.
Okay.
So this was proven by Mark Gendry. Picture up here in the corner, yeah, you see the reference down here. So this is already like old stuff, 2012. So it is an extension of what we call nowadays the polynomial method. So this is kind of a quantum trick, and it goes like this. I kind of try to give you a high-level idea. So the realization is that if you do this, if you take an attacker that has oracle access to this F, sampled from this function family, then you can observe, and this is what Mark did, that this probability is a linear combination of some fixed quantities. And these fixed quantities are just a bunch of real numbers, kind of for every xi and yi, you will get a real number, namely this probability, namely that F maps this xi to yi. And these here are two q relations that you want to fulfill. So yeah, it takes a bit of staring at this to kind of get a feel what's going on. But once you see that this is true, then you easily see that this theorem must be true, because by the definition of 2q-wise independent function family, it means that these are exactly the probabilities that are fully random. They're both fully random for a fully random function, but also if you just sample from this 2q-wise independent. So there's 2q values, and that was exactly the definition of being 2q-wise independent, is that these orbits, these probabilities behave uniformly at random. Yeah, so if you kind of believe this lemma by Mark, then it's immediate that this theorem also holds. So that's the end of the proof, but I still, of course, have to show the lemma by Mark. So that's on the next slide. So why is it true that these are linear? Why is this probability linear combination of these quantities? I'm just going to illustrate it for the case of one single query. If there's more queries, you have to work harder, but already that is a bit of formulas. So I want to show, well, it's going to look something like that. So you have an adversary that makes one query to F. So it starts with the all-zero state. It does a unitary transform. That's, according to Giulio, the only thing that we are allowed to do in quantum mechanics. And then it makes one query, so it ends up with some, say, 3 registers, X, Y, and Z. Z will just be preserved. X is kind of the input to the evaluation of F, and Y is the usual thing where the answer F of X will be XORed onto. And then there's some post-processing you're allowed to do, A1, and you measure, say, the first qubit. It doesn't matter, it could also be one of the other qubits. And then it's just 0, and it outputs a single bit. That's what this adversary does. And I want to argue that the probability to get a 1 in here at the end, when you do this, is a linear combination of these numbers. So these are just real numbers. And, well, you can write it out. So we do the same strategy as Pierre-Alain was doing. We basically look at the state after every operation. So in particular, we have an arbitrary state after A0. This is this. So it's just some arbitrary complex coefficients. We don't know what they are. And then once the oracle is applied, well, it transforms the Y register to Y XOR F of X. So again, it's still a pretty arbitrary state after this. And now you do a little bit of rewriting here. So you realize that you want to kind of make these probabilities here appear. And so you can rewrite this, we could just rename this thing to be y prime. And if you do one more step, well, you will actually see that these quantities, these betas here, they appear. So basically you can rewrite this in terms of betas. So I'm not expecting you to follow all the details, but again, you could look at the slides afterwards. But it's also, there's like no deep magic going on, but it's the kind of, these are the kind of linear algebra computations you do when you work in quantum stuff, quantum cryptography. And well, that's it. You end up seeing that, well, if you measure the state, well, it matters what these beta quantities are here. And there's one more thing. The probability to actually get a 1 is not just going to be the amplitude, which is here, but it's the squared of the amplitude. So it's not only one of the beta that matters, and that's why you not only have an x and y, but you have an x1 and an x2, y2. So there's two of these quantities that matter, because you have to get the probability, you have to like square the amplitudes. And so, yeah, this shows that for a single query, actually this lemma is true. And if you do more queries, it will just like, you get more betas involved. For every query you do, for every time you call this oracle, you will get more involvement of beta. But yeah, that just expands this thing. Yep.
Small question, why are these x's and y's now real numbers? Weren't they kind of bit strings before?
They are bit strings.
Okay, because I think you said real numbers. Okay.
No, they're not real numbers. They're
okay,
bit strings. What is real is, of course, these probabilities. So the betas, the coefficients, here they are complex, and these betas are just probabilities, so they are real. But the x, y, and z, those are bit strings, yeah, kind of indicating qubits.
Questions in the second equality, the sum alpha xyz, f seems to be something fixed, and on the right-hand side, it appears in a probability, right? So it seems like the left-hand side expression is a random variable, since f is chosen at random, right? And on the right-hand side, it seems to go away, right?
No, it shouldn't. I think f is indeed chosen random, but I'm not using this anywhere.
Does the probability go over f?
Yeah, it's the same probability here.
Okay, but on the left-hand side, I mean, there's no probability over f. F just is there, right? F just appears in the expression. Sorry. Yeah,
but I'm introducing this sum over y prime. So I'm just basically renaming the f of x to y prime. And this is also what's y prime now. So, and I'm summing, so...
But then, I mean, on the f is chosen at random, so on the left-hand side, you're having basically a mixed state, right? Because f is chosen at random, and what happened to this mixed stateness on the right-hand side?
Yeah, okay. I think there, to write it down properly, you do have to write mixed states. Yes, indeed. So, yeah. So yes, you're probably right that it's not a super clean equality, but kind of in spirit, it's definitely what's happening. Yeah. But if you look at the actual proof in January's paper, you will see mixed states, and you will see in appendix like very long formulas. So, yeah. Yes, Shweta.
I actually had the same question. So maybe like since we're talking about it, could you just clarify a little more? So the left-hand side equality of the equality, what should it be?
So here.
Yeah, what should that be?
Yeah, I guess if you wanna take into account that the f is sampled from here, then you would have to take the mixed state. So a probability over that you choose that particular f, and so it's just an additional sum over f.
Oh, okay.
And then of course you have to write like the bra and the cat, so it just gets very long. But otherwise, nothing really changes. Okay. Yeah. Yep. All right. Okay, so I think this is this was the first trick. Yeah, it's just like to recap again. So if you have the lemma, then you can see that, well, maybe now you have a better idea why this is the case. So like for every query you do, you kind of get more of these probabilities involved. But if you choose f to be from a 2q-wise independent function family, well, then these probabilities are actually the same as if in the case where f is picked fully at random. And that's why you can kind of lazily sample a random oracle also to a quantum attacker. So in the QROM, you can also do, well, it's not actually, yeah, no, this we'll see later. It's not lazy sampling, but it's at least you can kind of play something to a quantum attacker that looks like a random oracle, if you know a bound on the number of queries. Yeah. All right, so let's switch to the second tool. So this is something that was introduced by Dominique Unruh, a picture of him up here in the corner. And it's slightly complicated to state, but I'm just going to dive directly into some illustrating example. And so we're going to look at also this example is by him, if you click on the link below. If you look at an encryption scheme, and I'm not specifying the details of it, because that would just like clutter things up, but the idea is somehow you have like a one-way function f that is applied to some randomness, and then you also evaluate the random oracle on this R, on this randomness R, and you use that to mask your message. So I didn't explain how to decrypt and what you actually do with the key, etc. But what you want to show, I think that is something that must be familiar to you if you've seen indistinguishability proofs before. So this is the standard game that you play in the NCBR game. So you sample a random oracle, you sample a random bit, you choose this randomness, let's say it's an n-bit string. Then the attacker can make oracle queries to the random oracle, and he will choose two messages, M0 and M1. One of them gets encrypted according to this bit B. So, and the encryption is what I described up here. So the attacker in this step 3 gets access to the encryption, which is f of r, and MB XOR h of r. And the attacker has to guess the bit B prime, and he wins if B prime equals B. So this is the standard indistinguishability game. No? The attacker can choose two messages, one of them gets encrypted, and they has to tell which one it was. So, and we want to show that this game is hard to win for the attacker. That would kind of mean security. And in the classical random oracle model, one way to do this would be to just say, okay, let us do kind of one modification of this game where we introduce another random variable y, and we use this y instead to mask this MB. So instead of XORing with h of r, in this game 2, the only change we make is that we now XOR with y. The rest is the same. So now it's pretty clear, because of one-time pad arguments, is that this y is just a perfect one-time pad of hiding MB completely. So there's no way to win this game, because y is just independently chosen randomness. It completely masks MB, and the y is not used anywhere else. So clearly the probability to win this game 2 is 1/2. Okay, so, and now if you could show that these two games are actually close, the probability to win these two games is close, then we're done, because we want to show that the probability of winning game 1 is close to 1/2. And in the classical random oracle model, you can do that. You can upper bound this difference in probability winning and the probabilities of winning these games by the probability that this HR is actually queried in game 2. Because somehow the only way to see a difference between these two games is if you query h of r. Also, if you never touch h of r, well then there's no way for you to kind of see a difference from a randomly sampled y on it. So only if the adversary somehow has previously queried h of r, well, then you have a way, possibly a way to distinguish this, well, from a random value. And then you kind of say, oh, okay, but I recognize something here. This is something that I happened to query before. But the R was picked at random to start with. So it's very unlikely that any attacker here can actually query h of r. So this probability is very close to 0, it's negligible. And therefore, we're done. because we cannot win this game too. That's with probability 1/2, better than 1/2. It's actually equal to 1/2 because of one-time pad. The difference between the two is close to 0, and therefore the probability to win the original games must also be close to 1/2. So typical argument you do in these security proofs. But now, of course, so that was easy. But now, what about quantum? No? So like, if we do this in a quantum random oracle model, we have to argue that, well, I mean, I don't know what we should do. So we need this tool, and that comes in now. Like, there's the one way to hiding lemma that does something very similar. So these are still the same games as before. It still holds that you cannot win this game. You can only win it with probably exactly 1/2 because of the one-time pad argument. And now comes this theorem. This is called the one way to hiding lemma by Dominique. That says the following. So actually, maybe I'll show you this game. So he defines a third game where basically you run the original attacker. And I think you run the attacker from it's just the AH. And you pick a random query that this attacker makes, and then you measure there. So formally, it's stated in the theorem. So fix a Q query adversary A that has oracle access to H. Let B, so this is the B here, run this A of H until the ith query, where you pick the ith query at random, just take one of the queries that he makes, and then you measure that, the query register. You kind of look as what the quantum attacker does at that moment. And then the theorem says that for random values x and y, the probability kind of, the difference in probabilities of these two things, where you have an attacker that kind of runs on x and h of x, or instead of h of x, a random y, well, kind of the probability to see a difference between these two is upper bounded by the number of queries and a square root of b. And the square root of, that is the probability that this b actually queries at x. So this is the place, kind of the crucial place where you change stuff in the random oracle. You change it from h of x to y. And, well, it's related to the probability that a random query of a of h actually looks at this x, related with the square root. Because if you have this statement, then basically this is the probability to win G1, this is the probability to win G2, and, well, if you can still argue that the probability that you actually query at this random position R is small, well, then you kind of back to the case before. So we can relate these two. We know this is 1/2. We know this is the thing that we want to bound, and we can bound this. So this is something close to 0. Then yeah, we can do this proof. So it's quite a bit of magic if you have seen this. So who has seen this before? Well, very few people. Okay, so you've been introduced to the one way to hiding lemma. So this has really been one of the major tools in providing security proofs in a quantum random oracle model, including for some of the NIST schemes. And there's many different variants of these one way to hiding lemma. So this is, I think, one of the original ones, but they have been also improved over time to get like more tightness in the parameters. Yeah, so far so good. Yes, still awake, still warm.
I want to ask about the motivation again. So this encryption scheme, this was just like an example of where we maybe would need a security proof and how this could work.
Yes.
Okay, because I was just thinking about this scheme and how to decrypt, and
I didn't show any of this. So somehow the key should allow you to kind of reverse f of r. So,
okay,
but that's not the interesting part for this to understanding this.
Okay, but I think it makes sense now. Okay, thank you.
This is really just an illustration of how to use this technique. All right, so now up to the final part, and these are compressed oracles. So this is really kind of the main major magic trick that has been introduced in the recent years that has also led to a lot of progress in this area. And to warm up, we're going to do another quiz question. So please try to answer this. So be careful not to show results. So the question is, what is the resulting state if you run this circuit? So you start with the all 0 state, Then you apply a Hadamard transform on the first qubit, and then you apply one CNOT gate. What state do you get? Oh, I do spoilers. So the choice was between like 0, 0, plus plus, 0, 0 plus 1, 1, and 0, 0 plus 1, 0.
Can I ask a question?
Yes.
In the meantime?
Yes.
Can you go to the slides?
Yes.
Go back.
Back.
Back. Yeah. So this looks like a typo, the right-hand side.
Where did you go?
Yeah.
You changed place.
Yeah.
Confusing.
Sorry. So probability BHXY equals X, I mean, you don't want to give X to BH, right? Because if you give it, it can...
Yeah, no, definitely not.
So that's just a typo.
Yeah, no, you shouldn't. This way, no. Here you mean?
Yeah, so what should be the input to...
The input, well, okay, so, okay, maybe they're not like direct inputs to this, it's more like it's specifying what game they play here. So it's not, I mean, B is doing what A did, and also here, I mean, yeah, it's not, right.
Yeah, so you're saying run it with these inputs? Like,
Yeah.
Okay.
Yep. Sorry, yeah. Okay, I think by now most people probably have answered and discovered that this is one of the, well, this is maybe the most famous quantum state that there is, namely the EPR pair, this one. So what happens if you do, I mean, I'm not sure if I have explanations, but yeah, so you can think of like the Hadamard transforms the first qubit into a 0 plus 1, and then you do and nothing happens on the second one because you don't do a register, and then you kind of copy that first qubit onto the second one. So whenever there's a 0, you don't do anything, but if there was a 1, then now also the second qubit becomes a 1. So you entangle, so this is really an entangling operation, so you get a fully entangled state. You get this EPR pair, which you cannot write as a tensor product of two single qubits. So this is the most famous entangled state you have, and I think later this week you will hear a lot about what you can do with these. So this was just a little warm-up. Now actually what I wanted you to learn and also remember is, so the next question, which I think also is in the quiz. So now let's really make sure we don't show the results. The next question is, what happens if you take the C0 specified up there, and you put Hadamards all over, like both on the qubits before and after, and you can actually interpret this thing of like seeing the C0 operation in the Hadamard basis, so in another basis. If you kind of switch bases first, then you do the C0, and then you switch again. So here are the 4 options that you're given in the quiz. Is it just going to stay the same? Is it going to switch like target and control? Or are there some operations left? Is it like the same, but then there's still Hadamards here? Or does it turn into a control Z operation? And I think a little hint is kind of this up here, but so now I'm really curious of who has seen this before, or versus lucky and guessing. Okay, we have a pretty much uniform distribution. Okay, so the correct answer is that it will actually switch target and control. So the correct answer is this. And well, you can, once you believe that this is actually the right description, you can, well, it's not that hard to verify. So somehow, like a plus is a 0 in the Hadamard basis, and a minus is a 1 in the Hadamard basis. So now it's kind of, whenever there's a plus in the second qubit, then nothing happens to the first one. So this remains the same as it was before. But when there's a 1 in the second qubit, then it switches from a plus to a minus. And here it switches from a minus to a plus. So this is really the definition of a CNOT, but the other way around, when seen from the Hadamard basis. So this is kind of the circuit. So if you remember something quantum about this talk, then maybe this is the circuit identity to remember. So if you look at the CNOT gate from the Hadamard basis, then actually the control and the target qubits, they swap. Okay, so what? Now we're going to use this. I think I'm going to skip this. So there's two crucial insights. Again, they were by Mark Gendry in 2018. So in order to deal with the quantum random oracle model, so I introduced compressed oracles, this compressed oracle technique. And yeah, there's two main ingredients. One of them is what we call a purification. So again, this is maybe not something that you have seen directly, especially if you have not seen quantum stuff before, but if you will ever encounter, for instance, security proofs of quantum key distribution, or almost any other quantum cryptographic protocol, probably also the ones presented later this week, this will be a crucial tool in proving the security of things. Because we like to work with pure states. So like Nico pointed out that in this proof before, we actually had to use mixed states, and that's always, it's a bit more annoying. And one way to kind of use pure states is if you purify everything. So you can just like artificially, or in your mind, or in the proof, introduce new registers that kind of compensate for the classical mixedness of states. So if you don't have pure states, then you have mixed states. The mixed states are just kind of probabilistic combinations of pure states. And so if you want to purify that, well, you just introduce a new register, and the whole thing is pure. And in fact, if you have the random oracle model, it's a very natural thing. And we were all banging our heads. Why didn't we think of that earlier? You could just introduce a function register. So if you have this, standard oracle where you evaluate a random function, well, you can introduce the randomness of this function as just like, well, having an additional register, and then sum over all possible functions. So this is huge. So for an actual random oracle from mapping n bits to n bits, I mean, you will have to specify whole function table, so you're introducing a huge register, but it's not something that you do really in real life. It's more like a proof technique. But why not just introducing an additional register of qubits that contains the function tables, all the functions, and you sum over these. So this is like a purification of the function that you evaluate. And in particular for a random oracle, well, you pick the function at random, so you can just initialize that register in the superposition over all possible truth tables. No, that's exactly a random oracle. Okay, and from an attacker's point of view, who doesn't have access to this register because it's just something that we kind of added in our analysis, this makes no difference. Whether we first kind of choose a random function and give that, kind of put that into the F, or we just like provide an additional input to that box, which is an F in superposition of all the functions. If you don't have access to this F, it's exactly the same thing. Formally, you could, if you've done this before, you can trace out this F register, and it would basically just collapse this thing back to a mixture over all possible Fs. And that's exactly what the random oracle is. It's just picking a random function. Okay, great. So we can do that. And now comes the other trick. So the other trick, I mean, well, first of all, what this actually means. So this F, as I said, is huge. So here's just a very small example where you have only, say, bit inputs. So your possible inputs to F are just either 0 or 1. And what you're going to do, if you evaluate this kind of extended box, is, well, if the input x is 0, we are actually going to XOR f of 0, that's the output of f, which is, well, that's in this truth table here. You kind of C0, you XOR that onto y. That's the definition of like how you evaluate this function. You should end up with y XOR f of x. So if x is 0, well, you have to kind of C0 with this. And if x is 1, you have to C0 with that. So that's just like what this box does. And now comes the trick. Remember the circuit identity that we discovered before. If you look at this same thing from a different basis, from the Fourier basis or from the Hadamard basis, then the order of the C0 changes. So I do nothing else than just like putting Hadamards everywhere. And what that means is I look at these registers now not in the standard basis, but in the Hadamard basis, or in the Fourier basis in general. And the only thing that happens is that, well, okay, now I rename my things a little bit, but basically the direction of the C0 has changed. So before it was, remember, maybe I show it again. Before I was XORing the content of this function onto y. So it's kind of, you do querying f means you kind of look at like what's the function value is and you write that onto y. But now, seen from the other basis, it's the other way around. Now all of a sudden, so in this picture, you actually XOR whatever is in this y register, now in the other basis, onto this function register. Yeah, so in the end it's just an entangling operation, as we say, because the C0s apparently entangle stuff. So it's kind of, well, in the original picture, you were kind of, the attacker, the adversary who was making this query was looking what is in the F register. Now he's also looking, but the looking is kind of expressed in the opposite way. Namely, now you write whatever was in this Y register onto this. Notice also that here, now all of a sudden there's zeros. Here there was f of 0. But because f of 0 is a random value, I mean it's a random oracle, so it's in a superposition of all f. Once you do Hadamards, it's just the all 0 state. So seen in the Hadamard basis, the superposition over all possible functions is actually the 0 state. So what that means on a very high level is that now, seen from that basis, is that the attacker or Eve or whoever does this query entangles herself with the truth table, and is doing that she's doing that in a very clean way. So if you look at it from the right point of view, then you actually all of a sudden see that that an attacker is writing something into these purifying registers, and we end up, well, Mark suggested to call this thing a database. And so what actually happens when you look at evaluating this function in this basis is that you have these database states, and when you make a query, you actually write some values into this database. So yeah, in particular, for instance, here, if you have x equal to 0, well, this eta value here will end up on this register. If x is 1, then this eta will actually end up here in this. Yes, question.
On the prior slide, why did applying the Hadamard on f of 0, for example, transform the state to 0? Like,
yeah, that's what the Hadamard does. So like Hadamard on all qubits is like the Fourier transform over Z2, and basically it maps the 0 state to the uniform superposition. And the other way around, it's reversible. So if you start with a uniform superposition here, which you do, because you look at the random oracle, you start with this uniform superposition over all values, and you do a Hadamard, you will actually end up with 0.
Okay, got it. So you're using like the random oracle as like a uniform superposition of states, basically?
Yes.
Yeah, okay.
Yes.
Thank you.
Yeah. More questions? So what happens, again on a high level, is that if you do multiple queries in this way, so in the Fourier oracle, then you actually populate this database. So every query you make, you write stuff into this database. And well, Mark also showed how to kind of deal with that, because as I said before, this database is huge. So there's basically, for every input you have a bunch of qubits, and you want to ideally keep this small, but they all start off in the 0 state. So what you can do is you can kind of compress it and only track the non-zero entries. So if you do that, then you actually end up with a manageable sized database. In particular, if you have only make polynomially many queries, then your database register is also going to be of only polynomial size. And in fact, this now finally allows for an efficient simulation of the random oracle to the adversary. So this is really kind of what corresponds to the random sampling or to the lazy sampling I showed before. So setting it up that way actually allows to simulate a random oracle towards the attacker, and even learn some values of learn kind of how the attacker interacts with this database. So this might really sound like magic to you, and it definitely also sounded like magic to us when we, or like to many of us at least, when we saw this for the first time. And well, by now we understand much better. I mean, for a long time we could not really believe that this is true, but indeed it seems to work. And there's a lot of stuff you can do with it. And since 2018 there have been a lot of follow-up results. Chris is going to talk about almost entirely, I think, about techniques that are based on this. So here's a very simple one. You can do query lower bounds. So that's a typical thing that you want to prove that if you have a quantum player making Q queries, then this should be hard to find, say, a pre-image of 0. So it should be difficult when you make only Q queries to find an X that is mapped to the all-zero string. And this is what you expect from a random oracle. It should be hard to find a pre-image of 0 or of any fixed value. And indeed you can do this using this compressed oracle technique. So here's a sketch. You kind of track the norm of the state that, well, if you let this player run, you simulate this compressed oracle to the player, and then you kind of track the norm of the state projected onto the database entry that contains such a 0. So it starts at 0, this norm, because it's empty. And then every query the adversary makes, it can increase it by at most some, well, negligible amount. And so even if you do Q queries, then this norm is at most, well, Q over 2 to the n of 2. And then, well, you have to measure to get it out. And so that's, you get the square of it. So again, this is a very, very high level, but somehow that's kind of the spirit of stuff you can do. And the cool thing is that if you use newer tools, for instance, from this paper here, then you can kind of abstract away the quantum reasoning again. So this is the typical thing that we try often to make it like as easy as possible to use these results to kind of build a framework around it that just allows you to reason more classically, because quantumly often that's not it's not very intuitive. So yeah, so this is something you can do. All right, I'm almost done. I've shown you these 3 tools, or introduced you these 3 tools. So T-wise independent function families. There's been quite a lot of work after that on so-called semi-constant distribution or small range distribution, like all tools that allow to kind of expose properly to a quantum adversary these random oracles. And as I said already over the second tool, I've shown you the basic variant. There's many more variants. And I think the PhD thesis of Jelle Don from Amsterdam is a nice overview of what you can do related to these tools about the Fiat-Shamir technique. And you will see in the next talk another application of stuff you can do. I think, yeah, here's a couple of applications. I think I will not dive further into details. I also had an open question, like major open question is like, how do you deal with permutations? So far we've dealt with like random functions, and we've kind of given an idea how to simulate those in the compressed oracle technique. But what about permutations? So how can we kind of lazy sample a quantum accessible random permutation, which you're allowed to query forwards and backwards? Again, classically, this is not hard. You could just, like, whenever a new query is made, you just sample a random value forward way. When a backward query is made, you check with the list of queries you already had, and you give the according answer, or again sample a new value, and you're good. But quantumly, For a long time, we didn't really know. If we knew, we could actually answer, for instance, the indifferentiability of SHA-3. So this would be very important to actually show quantum security of this sponge construction, which is the underlying construction, a little bit similar to Merkle-Damgard, but also slightly different. And we would need some compressed permutation oracles for that, as far as we know. But there's been very recent result, literally on Monday. The next speaker, Chris Vines, and also our first speaker today, Giulio and Michael Walter, they have posted a new paper on the archive where they at least take a first step towards solving this problem. And Chris told me yesterday that he thinks these techniques they might also allow to prove more, but yeah, it's not that easy. So have a look at the paper and query Chris about it if you're interested. All right, so I think that's it. I'd like to sum up. I've spent quite some time explaining you more details about the classical random oracle model. I hope you got an idea what it is and what we can and cannot do with it. And also, hopefully, I convinced you that if you want to improve post-quantum security against quantum attackers, then you actually have to allow for superposition access to these random oracles. And that makes things quite a bit harder to actually prove. For now, well, I've shown you these three tools: TOIs, independent functions, one-way to hiding lemma, and finally the compressed oracles. Never forget about the circuit identity. I think they might come in handy at some point. And then, well, if we could, well, I think there's many more things to discover in this area and hopefully lead to establishing quantum security of more constructions. All right, thank you very much. I'm happy to answer questions. Also feel free to leave comments here that I will not display, so these are like private. Questions?
Any questions? Yes, we have a question over there.
I'm just curious about the timeline on these things. Like, there's this NIST, standardization effort. Like, how did they do like security proofs before they had some of these results? Or like, I'm just curious on the. Yes.
So I think in practice, what people do, they are just like happy enough with the random oracle proof, with the classical random oracle. And so there has been efforts, a lot of efforts actually, to establish quantum random oracle security as well. But well, I mean, in the end, the parameter choices are anyway not what the security proofs tell you, but it's always like a trade-off of having like practical parameters. So I think the choices of the parameters are not really taking into account this quantum random oracle security. I'm not sure if this is accurate. Probably Chris knows more about that, but yeah, I think basically people are happy enough with the ROM proof, even though, I mean, in principle, they should. We should also prove security in a quantum random oracle model.
Probably most of the current submissions don't have the QROM proof.
I think they usually don't come with a QROM proof at the beginning, but those are usually established after that, because you need some experts to look at that.
Okay.
Yes, Chris.
Maybe just one more historical remark. So for the most part of the NIST competition, it was not clear yet whether there is actually a separation between the random oracle model and the quantum accessible random oracle model. That only came towards the end of the NIST competition, where it was shown that there exist schemes that are secure in the ROM, but insecure in the QROM.
Yes, maybe I should have mentioned that, definitely. Indeed, so for a while we had the hope that whenever you have a classical ROM proof, you could also upgrade that to QROM, maybe losing some queries, some factor queues or some square roots in the way. But yeah, I think we don't have this hope anymore for like a generic upgrade, because as Chris said, there's a separating scheme.
Okay, thank you.